Okay, let's get started. In the last class, we were looking into the Low-Reynolds number models, right? LRN models. So we briefly discussed the near wall behavior on the two-component limit of turbulence and how it can be addressed using LRN models. We'll see it today. And we did a Taylor series expansion to see the near wall behavior for the three fluctuations, which gave U prime and the higher order terms, basically a Y dependency, and then for the V prime it had a Y square dependency, the near wall region, and W prime has Y dependency again. This we saw. So now we would like to introduce the same concept into the modeled equation and exact equation. So we will go back and see what is the exact equation that we have. Recall that if you take a K epsilon model, the epsilon, we did not take the exact equation to model epsilon, right? So we go back to only the K. The only K equation has an exact equation and its modeled counterparts. So we go back to taking the exact and model counterparts for the K. Okay, so let's take the K exact equation. K exact equation. So if you recall, it will be dou K by dou T plus Uj bar dou K by dou Xj equal to, the right hand side you have the three terms, which is dou by dou Xj of the pressure diffusion the turbulent diffusion and the viscous diffusion. And the production rate term and the dissipation rate term. This is your exact equation, K exact. And we also have the K modeled equation. On the left hand side, it's the same thing. No difference in the modeled and the exact equations. Left hand remains the same. Only on the right hand side, this particular term was not modeled. This was not modeled. You can recall the arguments that we placed, right? So only the this particular term is modeled, the turbulent diffusion term. So we will see the modeled equation here looks like dou by dou Xj of basically the nu plus nu T, or since we are writing it this way, we can write it nu T by sigma K plus nu dou K by dou Xj, or you can simply write it two parts here as nu T by sigma K dou K by dou Xj plus nu dou K by dou Xj. So only this turbulent diffusion term is the model counterparts exists between the two equations. The pressure diffusion is never modeled. Viscous diffusion looks the same, so I don't have to do anything about it. It will have the same behavior. So we look at only terms which are modeled here. Okay. Then I have this production rate term, which is, of course, we will have the what to say, the Boussinesq is used. So I will have plus, sorry, so I have plus 2 nu t Sij minus 2/3 k delta ij dou ui bar by dou xj. Okay. So I also have this particular term now. Modeled. I'm only highlighting using green color what are the terms that are modeled that we need to focus on. The rest remains the same between the two comparison. And here I have simply, I said it is epsilon, where we solve another equation for it. Okay. So with this, now we go ahead and apply this for a canonical turbulent boundary layer using the same condition, statistically stationary, homogeneous in two directions. So if I applying this to a canonical turbulent boundary layer, that is smooth wall turbulent boundary layer. So we have statistically stationary, it is dou by dou t of your average terms are 0, and then also statistically homogeneous. In two directions, that is x comma z, which implies we have, which means dou by dou x of all the average quantities and dou by dou z of all the average quantities are 0. The same conditions, and fully developed also. Fully developed, giving you V bar equal to W bar equal to 0. So if I use that condition and look at the near wall behavior using this the three equations that I have here. Okay. So I would get this equation, let's call this 1 here, and this equation 2. 1 is the exact and 2 is the modeled equation. So this reduces to, I will not look into the left hand side part, or I will only look into the terms that are modeled and its exact counterpart exists. Okay. So the equation would be like the first term, the diffusion term here. Okay. So I would write this as exact. So I have the diffusion term, right? So that is minus half of, I have ui prime. So if I expand it, I get u1 prime plus u2 prime. This is sum of three terms here, plus u3 prime multiplied by the uj prime that is there. Okay. And obviously I am looking into the y dependency. So dou by dou y term is what I am looking into. So this j will take 2, right? Not the other, this particular one, it's a dou by dou x and dou by dou z of all the statistical terms are 0. Statistically stationary, statistically homogeneous, right? So only dou by dou y, which is dou by dou x2 basically, right? This is dou by dou x1 and this is dou by dou x3. So only dou by dou x1, dou by dou y or the dou by dou x2 term survives here. So that means j has to take 2 value. You understand this? This is clear? This we can expand it. Since j is repeated, I is also repeated, so it eventually becomes a scalar, right? Sum of all the terms, and j I am taking it as 2, not 1 and 3, because when I take j as 1, it becomes dou by dou x1, and dou by dou x1 of this statistical quantity, this is an average quantity, is 0. Similarly, dou by dou x3 of this statistical quantity is 0. Therefore, here only dou by dou x2 term survives. Since dou by dou x2 survives, it becomes, j becomes 2. Okay, so this becomes only 2, which is u2 prime average, right? Statistically homogeneous, that is your, the other terms, dou by dou x1 of this is 0, dou by dou x3 of this term is 0 here. Only this particular term is surviving. Okay, and if I look at this particular term, exact one, what is its y dependency now? I can rewrite this as in terms of your uy. For consistency, I can write this as u prime v prime, okay, plus this is v prime plus w prime v prime. These are the three terms here. For consistency, I am writing. Now, if I look at this particular, let's call this equation star here. So, what will be its y dependency? The exact term of the turbulent diffusion term here. Yeah, u prime is y dependency, another u prime y, and v prime is y square. So, it is y raised to 4, right? So, this will have y raised to 4 near wall behavior. Okay, the exact term only for this particular term I am looking at here. So, since I am looking into that one, let's look at the exact term also for the, so the model term also for the diffusion, the turbulent diffusion. So, now I have the model term here. So, if I take model term, which is nu t by sigma k dou k by dou xj. Again same thing, dou by dou x1, dou by dou x3 will be 0. Same argument as above here, right? The same thing. So, only dou by dou x2 survives, j has to be 2, right? So, therefore, this reduces to essentially nu t by sigma k dou k by dou x2. And for consistency, if I write in xyz terminology, I get nu t as your, in a k epsilon model, you have c mu k square by epsilon. Of course, you have sigma k here, and then you have dou k by dou y term. Okay, so we look at only the k epsilon and the gradient of the k here. So, k square we have already figured it out in the last class, right? So, here if I write it again, so the k is your half of u prime plus v prime. This we did in the last class, w prime. So, I get here order of magnitude of y square, because this will be, this is y square, this will give y raised to 4, and this is y square. So, to first order, this gives me only y square behavior. Okay, fine. So, now k is done. We also have epsilon. Okay, so we need to also figure it out what epsilon would do it. So, let's see it here for the epsilon. Yes. So for epsilon, let me use another color. Okay, for epsilon now it is nu dou ui prime by dou xj square average. So upon expanding this, I would get sum of 9 terms. Okay, all 9 term survives here because it's the average of the two fluctuating quantities. So it's a correlation term. So but we are looking into the y dependency. So in the sublayer, the gradient dou by dou y will be much larger than dou by dou x. Okay, so this is of course sum of all the terms. So if I rewrite this, if I expand it first, I would get, let's say, nu dou u1 prime by dou x j whole square plus nu dou u2 prime by dou xj whole square plus nu u3 prime by dou xj whole square average. So in the sublayer or in the near wall region, what is so special in this part is that you will get typically your dou by dou y gradients are much larger than your dou by dou x and dou by dou z or dou by dou x2. If I write it in terms of that, it is basically dou by dou x2 much larger than dou by dou x1 or dou by dou x3 gradients in the near wall zone. This y gradients are much larger in that, and therefore this particular term will take up. So epsilon will be essentially, the j will take 2 dou by dou x2 of these 3. So which is nu, for consistency I am writing it in terms of dou u prime by dou y square average plus nu dou v prime by dou y square average plus nu dou w prime by dou y square average. So what is the near wall behavior here? So dou u prime by dou y, if I go back here, u prime is y dependency, dou u prime by dou y will give me no y dependency, right? So dou u prime by dou y gives me no y dependency, and v prime will give me that. So this will give me no y dependency, y raised to 0. Okay, but dou v prime by dou y, that is y square, so it will give me y behavior, but to first order it is only y0. So this becomes the higher order term here, this is y, and this is again y0. That makes it essentially, so this will be the higher order term here. So what does this mean? Epsilon is having the y0 behavior. Epsilon has no y, it is not showing any y dependency, okay, in the near wall zone. So epsilon is available now for the model, k is available, and the dou k by dou y will figure it out. So I get essentially the near wall behavior k square, right? So k is y square here, right? So I get order of magnitude of y square, so y raised to 4 by, I have y0 for the epsilon, and dou k by dou y will give me order of magnitude of just y, because k is y square. So this is giving me So the near wall behavior of the modeled term here, okay, which is here. If I take this, it is giving me y raised to 5 behavior, and if I take the exact one, this is the exact one, it is giving me y raised to 4 behavior in the near wall zone. Something is not correct, right? So we must do something about it. So it looks like dimensionally the model is consistent, the K epsilon model, the standard K epsilon model, but as you approach the near wall, very close to the wall in the linear sublayer, buffer layer, where viscous effects are dominant, it is not accounting for, as I said, the 2 component limit as well as